So I wanted to help you if you're struggling to choose the right equation for our quiz calculations or just in general on page 12 and maybe in the future on our test. So these are the three major gas calculations that you're going to do, the three major equations that we have. And technically there are two more that we're going to talk about shortly, but they're just variations of the combined and the ideal gas law that we see here. So this is what we need to focus on to get the basics of. Now, the first law that we learned about was that combined gas law. This is the one that we had the equation for written on page 3. It's the one with the P1V1 over N1T1 equals P2V2 over N2T2. And we have these 1s and 2s on our P's, V's, N's, and T's because there is a change happening to our gas. This one side of the equation is for the first situation before the change, and the two side is for all of the numbers and measurements that were taken after the change. And the whole idea here is that I had a gas and something about it is changing, and I want to be able to predict the rest of the results. So if you're looking at a question, this is the most important thing to look for is there a change? Because if there is, you automatically know you're using the combined gas law. Now, if you're not seeing a change happen, then most of the time, that's actually going to end up being the ideal gas law. Here, nothing is changing. You'll notice that the equation has basically the same variables that we saw up there in the combined gas law, that P, V, N, and T. Remember, this is a special R that we only use in this ideal gas law, and you will need to go back and look at page 9 to learn more about it and maybe watch that podcast over it. But it has the same variables as the combined gas law, but there's only one of each. And they're in some weird places and whatnot, but here there's only one of each because nothing is changing. So that's what we're looking for when you read a question, is look for some kind of verb, some kind of change. It says that we've got a gas and then we took it to the top of Mount Everest. That's a change. It might just say something like, and then the volume was increased. What's the new pressure? That's a simple change, but no matter what, those combined gas law problems will have a change happening. Now, the Dalton's law, gas law, is kind of the odd man out. It's a special, the full name of that is Dalton's law of partial pressures, and that's all that Dalton's law really applies to, is pressures. So most of these problems don't even give you a temperature and a pressure and a volume, let alone moles. So it's mostly going to be if you see a problem that's all pressures, but specifically if you see something about a total pressure or partial pressure, that is a definite indicator that that is a Dalton's law problem, that we're going to be just adding up the partial pressures to find the total, or subtracting out some of the partials we know to find the partials that we don't. There are some special cases that have some percents in them, but that is the main three. Now, these next two that we see here are those special variations of the combined and ideal gas law that Mr. Avogadro came up with. And this first one is only when we have two gases at the same temperature and pressure, which would mean that really what we're looking at is two separate things that we're comparing. So we got the one side and the two side, but because the temperature and the pressure are the same, they're not different. Remember in the combined gas law how we can leave out anything that's not changing. This is really just a special situation of that combined gas law here. So it's not something completely new and different. You will see a change happening here, and I will honestly accept if you say that this is a combined gas law problem when it's an Avogadro's problem, because it really is the same principle, just applied to a slightly different situation. But there still, we're going to see two volumes or two sets of molecules or moles. We're seeing two of anything, or it's talking and comparing those different things, how it's changing substances there. That's a change still, and that's going to be that 1-2 equation. And then this last one is actually a special version of that ideal gas law. Go back and watch the podcast if you're curious how. But this is only when we have a gas and it's not changing. So once again, not changing. This could be worked out with the ideal gas law. But as long as we are at STP, as long as it's standard temperature and standard pressure, then that would standardize most of our equation, which lets us simplify the work we're doing into a simple dimensional analysis problem. Only if we're dealing with liters and moles, and only if we're at STP, and only if things are not changing. So there's a whole lot of ifs. We don't use this a whole lot, at least until we get to that stoichiometry stuff later. But at least here in this quiz, if you see something that's not changing and you're at STP, this might be the shorter way to work it out. So if that's all you needed was a refresher on the basic types of equations, then you can stop right here. What I'm actually going to do just super quick is look at the quiz review problems and go through each of these because they are remarkably similar to your quiz problems, and go through that choice, that process of choosing which equation it is just very quickly with you so you can see that process happening and understand a little bit better how some of these very similar questions on the quiz got chosen to have those specific equations. So this first one is asking us to calculate the new volume. And already, if I'm paying attention and if I'm really looking for a change like I should be, that's the real first thing I should ask myself with each of these questions, is I already know there's going to be a change because it's mentioning new volume. So I'm willing to bet because there's a change, this is combined gas law, and that is correct. As I continue reading, I have a volume, temperature, and pressure given to me, and then it says that it is being converted. That's changing the conditions to our standard temperature and pressure. So this is going to help us find our standard temperature and our standard pressure back on page 3 of our packet, which means that that's going to give us the second temperature and pressure we're going to need, because yes, anytime we have a change, this is the combined gas law. So this is that P1, V1, and 1T1 situation there. Now in the second one, do we see a change happening? Well, it's talking about a 5-liter sample of hydrogen, has this many moles, and then it gives us another volume, a 15-liter sample, the same temperature and pressure. It's just that it's carbon monoxide. So our substance has changed here, and our volume is changing. More importantly, we have 2 volumes given to us here. It looks a little different than that last problem, though, because the substance is changing too, and really all we have here is our volume and moles. It's not all the rest of these crazy numbers. So this is technically could be called combined again. I'd accept that if you used it and wrote out that equation as your base, but technically this is Avogadro's principle, where we just have the V and the N involved in things. Just simplifying that down. Now, in question number 3, as we read through it, we see some very important keywords, or else we should see some very important keywords. It says to calculate the partial pressure if the total pressure inside is 865. As soon as I'm seeing those words, this has to be a Dalton's Law problem. So this is probably going to somehow, somewhere involve some kind of finding a total where I'm adding up all the other pressures, or if I have some of these pressures, then, and the total, then I can subtract them out to find one that's missing. So, not quite last. Question number 4 here. 5 grams of chlorine gas is introduced into a container at 25 Celsius. What's the pressure in the container? Well, that's not really a change. It says I've got a gas, it's in a container. I've got this volume, temperature, and pressure, but that's just one of each. There's not another one. And even grams over here, I'll use this to find moles, but that's N. So I only have one of each thing. Nothing is changing, and that means this is our ideal gas law. And now, last but not least, question number 5 asks us to calculate the mass of ethane that occupies a gas volume of 10.4 liters at STP. So, is anything changing here? No. So, technically, we can be using the ideal gas law, and this will get us a perfectly correct answer if we use that PV equals nRT. Just keep in mind the only number we see here is our volume, the temperature, and the pressure, kind of like in that first one that said it was converted to STP. We had to go back and look at page 3 in order to find that standard temperature and pressure that we're going to use here. But if we notice we're at ideal and at STP, then that means that we have another option. We can use Avogadro's special shortcut for the ideal gas law, that 1 mole equals 22.4 liters. And especially since we're going to be needing to find the mass anyway, we're going to need to find moles here in this equation. If we were doing it this way, solving for moles opposite over neighbors, RT, we'd get moles out. We'd still have to do some dimensional analysis to turn moles into grams and get our final answer. If we use this, when we're at STP, it just means we're going to start with the liters and have to do another step in between before we do this down here to get our grams. But this step is a pretty nice, simple step compared to this, at least in my opinion. So, hopefully that helps you understand the choice of equations that you're seeing here, as well as on that answer key. So don't forget to look over all of that. I know that we have a lot of resources there on that module, but this is probably one of the most useful for problem solving. Now that we know what equations we use, and I've helped you kind of figure out each of them, this is the way I've actually finished out each of these problems. So now hopefully you can follow along. I've shown you every single step of the work, even my cross multiplying here. In problem 1, when I circled this green diagonal, that's that green number, 1433250 underneath. So I've shown you all of my work, dividing by the number to get that last value there. So if you have any questions at all about how or why I did things here, how or why the quiz questions you were working on turned out the way they did, then let me know. I hope this helped.